Tough guy, yeah.
Let's start. So today we are very happy to have Tim Linden from Ohio State University. So Tim is a rising star in our field. He got his PhD from UC Santa Cruz, and then he got the Einstein Fellowship and working as a Kennedy Fellow at the University of Chicago. A few years ago, he moved to Ohio State University. So Tim is a real expert on both high-energy physics and astrophysics. And today, he's going to tell us about the leptons, pulsars, and gamma rays. Let's welcome him.
Thanks for having me here today. Today I'm going to argue for a new model of the Milky Way at TeV energies. It's a paradigm where it's high-energy electrons and positrons, rather than cosmic ray protons and antiprotons, that play a pivotal role in shaping the dynamics of Milky Way-like galaxies throughout our universe. This isn't due to some big theoretical leap or anything like that. Instead, I'm going to argue that recent observations force us into these new conclusions. And the observations I want to talk about are shown here. Two objects that I will call TeV halos. The one on your right is the TeV halo that surrounds the Geminga pulsar. The one on the left is the one that surrounds the monogem pulsar. Both of these are bright, spatially extended gamma ray sources that are centered on the positions of known pulsars that are near Earth. So what are we talking about when we talk about gamma ray sources? We have an electromagnetic spectrum shown here. We have the visible light somewhere in the middle of that picture, the things you can see, with an energy of about 1 eV. We have X-rays, photons, things that you go in an X-ray machine when you break a bone. It has an energy of about 1 keV. And then today we'll talk about gamma rays, and not only kind of wimpy gamma rays like the MeV stuff, we'll talk about gamma rays that have energies of a TeV, or 1 trillion electron volts per photon. Now, those sort of extremely intense gamma rays are made by extremely energetic cosmic rays. And they can be made by hadronic processes or leptonic processes. The hadronic process is shown on the left here on the bottom. That is a very, very high energy proton with an energy of many, many TeV hitting an atom of, say, gas somewhere in the galaxy. And when that happens, it's a really high energy proton hitting a really high energy gas proton or neutron, and that produces a hadronic interaction, just like you'd see in something like the LHC. It produces a jet of material. Some of those jets decay to pi zero, some of those decay to gamma rays, some of them decay to more protons and antiprotons and electrons and a whole mess of events that comes out. There are also leptonic processes you can see on the right. This is, for instance, inverse Compton scattering. A low energy photon, such as something from starlight or from the cosmic microwave background, gets hit by a very, very high energy electron. Again, the electron has an energy of many, many TeV. When that happens, they exchange energy, and that accelerates that photon up to a gamma ray photon that itself can have GeV or TeV energies. That's the main process we'll be talking about today. How do I search for these TeV gamma rays in the sky? There are a few instruments. One of them shown here is the Hawk Observatory, which is in Mexico, just south of Mexico City. It is a bunch of water tanks on the ground. There are 300 of them shown there. They are big. You can see some cars and trailers in the background compared to the size of the tanks. What happens is a really high energy gamma ray comes in. It hits the atmosphere. When it hits the atmosphere, it produces a huge shower of energetic particles. Some of them are charged particles. There are electrons, positrons, more gamma rays, neutrinos, light. That all goes through these water tanks that are at a very high altitude of about 5,000 meters. And when it goes through the tanks, it's picked up as Cherenkov light within the water tanks. And by noting which tanks get hit, when they get hit, the order they get hit, I can tell how energetic this gamma ray was and where it came from on the sky. This is also done. This is a water Cherenkov technology. It's also done with atmospheric Cherenkov telescopes, like HESS, shown here. Again, a really high energy gamma ray comes in, hits the atmosphere, produces a bright shower that can be seen. And what these telescopes are is sensitive optical instruments that look for that Cherenkov light moving through the atmosphere. They pick it up as optical instruments, tell where that shower is moving, where it came from, what its energy is. So this is the HESS technology in Namibia. This is the Veritas detector, which is in Arizona and has a lot of local expertise here. These are complementary technologies in that Veritas is in the north, so it sees northern hemisphere sources. HESS is in the south, sees mostly southern hemisphere sources. And for many years, these things have been operating for more than a decade among these different experiments. HAWK only for about the last 5 years or so. And so they've seen many of these TeV emission sources surrounding young and middle-aged pulsars. Why are we just talking about this today? Why aren't we talking about this story a decade ago? And why do we now know that these sources are important? It's because previously we were living in what I'll call the hadronic fairy tale. And the hadronic fairy tale is as follows. It's that most of the cosmic ray energy in our galaxy, or in galaxies like the Milky Way, comes from hadronic processes. And by hadronic processes, I mean those powered by cosmic ray protons. And that had a lot of support. It's what we see when we look at the sources of high-energy cosmic rays. Things like supernova remnants shown here are modeled to produce mostly cosmic ray protons, with only about a 1% contribution from cosmic ray electrons at energies of a few GeV. It's what we see when we look outside of our backyard with cosmic ray detectors like AMS or PAMELA that float around in space and directly observe cosmic rays at GeV and TeV energies. Again, these are observations by AMS. They see mostly cosmic ray protons and only about 1 in 100 cosmic ray electrons, comparatively. This is what we see when we do models of what produces most of the gamma ray emission at GeV energies, observed by instruments like the Fermi Lat, again in space. So at GeV energies, we have some model for what the diffuse emission looks like in our galaxy. And most of that, again, produced by cosmic ray proton processes. Here's the data. Here are the cosmic ray protons. And the cosmic ray electrons are that green line, again, down by about a factor of 100. And in addition to fitting the different observations we see, there was a very good model for this sort of story. We start with some source of relativistic cosmic rays from our supernova remnants. Those things propagate, and they diffuse. And the way they diffuse is they move around in magnetohydrodynamic turbulence. There's a bunch of magnetic fields throughout our galaxy. They're bouncing around in those is a diffusive process. It can be modeled with this nasty equation here that can be solved numerically. And so as they're moving around through the magnetic fields of our galaxy, they keep propagating. Sometimes they propagate until they get to Earth. And if they get to Earth, they're detected by instruments like AMS or PAMELA. Or sometimes they don't make it all the way. They hit gas, or they hit interstellar light along the way, and they have an interaction, which moves that energy into gamma rays that we can see, right? The hadronic processes or the leptonic processes from before. And if they do that, they produce gamma rays that come directly to Earth and can be observed by instruments like the Fermi Lat, shown here. But even a decade ago, there were a few cracks in this very nice story I've set up. The first was determined by the Milagro experiment. Milagro was an older predecessor of HAWK. And Milagro found an excess at TeV energies compared to those best fit models from hadronic cosmic rays. So here are the Fermi Lat data points shown here at GeV energies. Right here, you can fit your curve to those. And because you know the cosmic ray proton spectrum, that's measured from instruments like AMS, you know what the spectrum of gamma rays is supposed to be up to very high TeV energies. That sort of fits the observations of 1 TeV, but there's this odd data point at an energy of 15 TeV that's shown with the little green circle. That data point is about a factor of 6 above any of the data, and the error bars are shown there. They're very, very small. The current model of hadronic cosmic ray emission doesn't appear to fit the diffuse emission that's observed throughout our galaxy at TeV energies. This is also true of the sources themselves. Most of the hadronic cosmic ray sources come from things like supernova explosions. But if I look at the HESS TeV sky and I just see what sources can HESS see at TeV energies, most of the sources are not supernova remnants. Here is their pie chart of source lists here. The supernova remnants here, there are 8 of them out of about 100 sources. Compare that to 12 sources that are produced by pulsars, leptonic emission sources powered by rotational pulsars. And then another number of about 40 sources that have not been identified. And that's weird because most supernova remnants are identified at many, many wavelengths, spreading from optical emission to radio emission. So only a small fraction of the sources are known to have a hadronic origin. And this is also seen in instruments like Veritas that find a number of sources that are powered by rotational pulsars across the Milky Way plane. On top of that, there's an even odder oddity in the cosmic ray electrons and positrons that do make it to Earth, something called the rising positron fraction. So I'll stop here to show the axes for a second. This is the energy of a cosmic ray electron or positron in GeV. So this is billions of electron volts. And the y-axis is the fraction of those that are positrons. So it's the antimatter fraction of the cosmic ray electron and positron flux. If something made 50% electrons, 50% positrons, this cosmic ray electron-positron fraction would be 0.5. If there was a universe that only had electrons, there was no antimatter, this would be 0. And what we saw was in the hadronic models, which are shown in this beige region, you expected it to start at about 0.2 or so and then fall off pretty steeply as you went to higher energies. Instead, models showed the opposite. The positron fraction started climbing again above an energy of about 10 GeV, eventually reaching a value of 0.2 or 0.3 again at energies of a few hundred GeV. We don't know what sources would produce these. Supernova remnants are supposed to produce mostly protons, and those protons are supposed to produce mostly secondary electrons and positron pairs with a large overabundance of electrons, and it's supposed to fall way down here. So in this talk, I'm going to argue for a new paradigm that solves these mysteries. I'll argue that electrons and positrons produced by pulsars actually dominate the Milky Way's energetics at TeV energies. And in particular, I'll argue that positrons produce most of the diffuse TeV emission and solve that Milagro puzzle. Also, pulsars produce the majority of the TeV sources that are observed by instruments like Veritas, HESS, or HAWK. Finally, pulsars are responsible for that rising positron fraction. To answer these points, what do we actually know about pulsars, right? Now, we have an ultimate energy source. We have a battery at the center of this problem, and the battery is the rotational power of the pulsar itself. So a pulsar is born spinning extremely rapidly. It's a 1.4 solar mass object that can be spinning up to nearly 1,000 times a second. That gives you nearly 10 to the 50 ergs of kinetic energy to play with. And as that, due to the magnetohydrodynamics of a very fastly spinning magnetic field, it is losing kinetic energy as dipole radiation and spinning down, getting slower and slower over time. So that kinetic energy has to convert to something. And what does that kinetic energy convert to? It can convert to accelerating electrons off of the surface of the neutron star. So the way this happens is I have a surface. It's mostly neutrons, but on the surface there's an atmosphere that has electrons and protons on top of it. I have a very strong magnetic field. The magnetic field can be 10 to the 10 Tesla, and it's rotating rapidly. So this produces a very, very strong electric field. And that electric field can accelerate an electron off the surface of the pulsar. And in this very strong electric field, I can accelerate that electron to energies of hundreds of peta-electron volts, or nearly 10 to the 18 electron volts. What happens when I have a 10 to the 18 electron volt electron inside a magnetic field of 10 to the 10 Tesla? I immediately synchrotron radiate a gamma ray, and that gamma ray itself has an energy of many, many TeV. And now I have a many, many TeV gamma ray inside of a very, very strong magnetic field. And what does that do? It produces an electron-positron pair. Those electron and positron pairs, this is the same story I told yesterday for people who were also at that talk, again get accelerated to very, very high energies where they produce more synchrotron radiation, which in turn produces more electron and positron pairs. At the end of the day, I start with one seed electron that I've boiled off this neutron star, and I produce nearly 10 to the 5 electron-positron pairs. I've immediately wiped out that electron-positron asymmetry. So if this was the only source of emission, I would expect the positron fraction is always 50%. The final spectrum of those electrons and positrons, once they escape from the pulsar, depends on that magnetic field model. But in fact, it doesn't matter too much, because right outside the pulsar, there's another thing called a pulsar wind nebula. And a pulsar wind nebula is a voltage drop that is produced via a termination shock. So I'm producing a huge wind of relativistic particles coming off this pulsar, and it pushes back the interstellar medium. If there's gas and dust around, they get pushed back because there's a relativistic flux of particles coming out. Eventually, the energy density of that flux drops, is r squared, and it falls below the value of the interstellar medium energy density. And when that happens, the gas in the interstellar medium of our galaxy suddenly becomes a brick wall, and it stops electrons and positrons from moving any farther. And when that happens, I get a significant voltage drop of nearly 30 petavolts, which means I can accelerate particles to, again, 30 PeV energies, extremely high energies at this point surrounding the pulsar. And this produces some really energetic electron population. There are models for these, and I won't go into them in detail here. But what I do want to do is just go and look at the observations in a little bit of detail. What do these pulsar wind nebulae look like at different energies? They've been observed for several decades at X-ray energies, at radio energies. Here is the pulsar wind nebula on the top right from the Geminga pulsar wind nebula. It has an extent of approximately 1 parsec. And that extent is explained by the dynamics that I just set up. I have a relativistic wind coming out with some energy density, and then it gets stopped by the interstellar medium. And the radius at which that happens is when the relativistic wind energy density falls below the interstellar medium energy density. And so I can calculate the radius I expect for a pulsar wind nebula, and it's about a parsec, and it scales positively with the power of the pulsar. More powerful pulsars can push the interstellar medium out for longer distances, and it falls inversely with the gas density, which tells you how thick the interstellar medium is. Note that that's a known physical mechanism and explains the size and distribution of these sorts of objects, and it anticipates that they would be on the order of about 1 parsec. Now, this is what's observed in X-ray observations and radio observations. The mechanism for this is that I have a lot of really high energy electrons, and I have magnetic fields in this region, and so they're synchrotron radiating and producing emission at X-ray energies, at radio energies, and I can see that. What happens at TeV energies? I should have a similar process, the leptonic process I described early on the slides of this talk. I have a very high energy electron with energies of TeV or PeV energies, and it hits some photon from nearby starlight, for instance, and it upscatters that photon, inverse Compton scatters that photon up to TeV energies where I can see it. So let's take our TeV telescopes, things like Hess, Hawk, Veritas, point them at these same sources, and see if we see this compatible emission, which should also come from the pulsar wind nebula at TeV energies. So we do that. We look with our telescopes like Hawk. And instead, what we see is this picture I showed you before. Highly spatially extended, bright TeV emission sources that are surrounding pulsars. But these are not 1 parsec sources, like we saw at X-ray or radio energies. The scale of these objects is many degrees on the sky, is the first thing to note. Here is the moon for scale. This is about 5 degrees across. That 5 degrees across is about 25 parsecs, which means in radial area, it is 25 to the 3rd times bigger than I would have expected for the pulsar wind nebula at X-ray or radio energies. It's a massively larger system than I expected for the pulsar wind nebula. And it has a lot of energy. The total energy of this Gaminga system here is about 10 to the 31 ergs per second, which is also about 10 to the 31 TeV per second. I look at the monogem pulsar on the bottom left, and I get very similar numbers. The total flux is about 10 to the 31 ergs per second. The extension of this source is about 25 parsecs. And remember, I'm actually seeing the pulsar wind nebula for these objects, and I know they're only 1 parsec in extent. This source is much, much bigger. This emission has a very hard spectrum. It doesn't trace gas at all, so the production mechanism is the inverse Compton scattering of starlight. It appears that this is leptonic emission, and I need to explain this size difference. I also look at these sort of sources with instruments like Hess, right, atmospheric Cherenkov technology, and I see a number of sources that are surrounding pulsars that produce bright TeV emission. In these sources, here's the spin down power of the pulsar itself. This is how fast the pulsar is losing kinetic energy. That also tells you how many electrons and positrons I think the pulsar is going to be producing, because faster spinning pulsars that are losing more kinetic energy, should be able to produce more electrons. And on the y-axis, you see the radial extent of these sources. It's not 1 parsec. Many of these sources are 5 parsecs, 10 parsecs, 20 parsecs, 30 parsecs in extent. Here, we go way above what we expect from the pulsar wind nebula. Moreover, I pointed out something to you earlier. In that picture of pulsar wind nebula, pulsars that are spinning faster, that have more kinetic energy, are supposed to be larger, because the pulsar wind can push out back the interstellar medium for a longer distance, right? Here, we instead see the opposite correlation. As the spin down power of the pulsar gets smaller and smaller and smaller, the source gets larger and larger and larger. The morphology, the energy dependence of this problem, is totally different than what we see at X-ray or radio energies. And this needs some sort of new morphological characteristic. So we now have not a 2-tiered system like we used to have, but we have a 3-tiered system. People knew the rest. The pulsar wind nebula is expected to be about a parsec. It's supposed to be a leptonic emission source that's produced when I have a relativistic wind of cosmic rays that's getting stopped by the interstellar medium, is getting reaccelerated, is producing synchrotron radiation. And that's seen at X-ray and radio energies. That's the pulsar wind nebula. We've known about that for 40 years. We had the supernova remnant. Supernova remnants are big and hadronic, cosmic ray protons that are escaping in a shock front after the supernova goes off. They should be hundreds of parsecs in radius for these large systems. And we've known about those for decades. But now we see some new morphological characteristic we can't explain. Leptonic emission with a scale of about 10 parsecs, larger than the pulsar wind nebula, smaller than the supernova remnant, and leptonic instead of hadronic. How do we explain these? Well, they must be some sort of new morphological feature. They're 3 orders of magnitude bigger than the pulsar wind nebula in volume. They have a different energy dependence. And the pulsar wind nebula, like I said, was connected to that physics of the termination shock. I know what happens when I stop a relativistic wind. I know how I build up that potential. I need some similar morphological description for these TeV halos, and that's why we give them a new name. They're a new physical object that requires a new morphological description. So we'll go back to this model later. But what do those TeV observations, just the data that's been taken by Hawk and Hess so far, tell us about the TeV sky? What are the implications we should draw? And to do that, you have to make some assumptions. You have to make an assumption about the energetics of different pulsars. We've seen Gaminga, we've seen Monogem, we've seen about 20 other sources with Hess. You have to assume that, so for the purposes of this talk, I'm going to assume that every pulsar converts a similar fraction of its spin-down power into electron and positron pairs. So for Gaminga, it turns out that this number is about 10%. 10% of that spin-down power is converted into electron and positron pairs at high energies. And I'm going to assume that that's true for a minute for all pulsars. This statement is well supported. These things aren't observed because they're particularly bright sources. They're observed because they're particularly close sources. They're, in fact, the 2 nearest middle-aged pulsars. And there are many similar Hess sources. And though I haven't shown this, they all have very similar efficiency fractions. It's about 10% throughout. And then secondly, you need to make some assumption about what pulsars actually exist in the Milky Way galaxy. And here there's a number of things. How often are pulsars born? What's the supernova rate in a galaxy like the Milky Way? What's the initial period that pulsars are born with? How fast do they spin down? What's their magnetic fields? You have to put in a normal model, but what we're doing for the rest of this talk is putting in a very normal model. This model comes from this paper here by Bates et al., the pulsar psi population community. I'm just going to take those numbers at face value and put them into this talk. And these numbers aren't made in order to do TeV halo calculations or even to look at pulsar wind nebulas. They're meant to fit the 2,500 or so radio pulsars that are observed throughout the Milky Way. Right? So they're a fit to that sort of data set, and they're just going to be applied throughout this talk to that data set. So these are the assumptions I'm making. But I've labeled them in red because I think they're about all of the assumptions that I'm making in this talk. So taking those, what are the implications of the observations that we have so far? Any questions? The first implication is that most of the diffuse TeV emission in the Milky Way is produced by TeV halos powered by pulsars. That is, TeV halos explain this data that I showed from the Milagro observations at 15 TeV. They explain this data point. How do I do that? I take the TeV halo spectrum for the Gaminga TeV halo. I calculate its intensity, and I calculate how bright this thing is compared to its spin-down power. I compare that spin-down power to all the pulsars produced throughout the Milky Way and their individual spin-down powers, and I put this on that plot there, and it looks a lot like this. So here again is the energy in GeV. Here is the Fermi data at GeV energies. It's fit very well by this hadronic story. Our hadronic fairy tale is shown in blue here. And that fits the Fermi data. It does not fit the data up here at an energy of 15 TeV. But I've just put down the TeV halo spectrum that was observed from Gaminga. I normalize that to the number of pulsars in the Milky Way, and I get this emission here. And now there are spectral assumptions. I also have to assume that most pulsars have the same spectrum as observed from the Gaminga TeV halo. But I actually don't have to observe that. I don't have to assume that at the energy of 15 TeV I care about. And the reason for that is because Hawk is actually measuring the TeV gamma ray flux at an energy of 7 TeV, which is right here. This is where everything is best measured. There are some spectral assumptions over here, but here this is just the normalization of the Geminga TeV halo itself and the number of pulsars I expect to exist in the Milky Way. I put that on the plot, I get the right answer. It's the number of pulsars whether or not they are oriented towards Earth. And that'll become important later. So they might not all be detected in radio. That's something that's in the pulsar population synthesis community, beaming fractions. Actually, we'll talk about that in just a few slides. Any other questions? The second implication from this study is that most of the TeV gamma ray sources are TeV halos. That is, most of those unidentified sources that were observed by Hess but have never been associated with any object should be associated with pulsar-produced TeV halos. And for this, you just need some somewhat simple numerology. We'll talk about Hawk sources first. The Hawk telescope, again, that's the Water-Cherenkov telescope on Earth, has observed 39 sources in their 2.5-year catalog. 5 of those 39 sources are coincident with the position of middle-aged pulsars. That is, pulsars that are older than 100,000 years. Why do I say pulsars that are older than 100,000 years? The reason is because by that point, the supernova remnant is gigantic and dim, and there's no possibility that you're confusing this with supernova activity. So these 5 sources are coincident with middle-aged pulsars, which means they're definitely being powered by the rotational energy of the pulsar itself. On top of those 5 sources, there are 12 more that are coincident with the positions of middle-aged pulsars. So right off the bat, 17 of the 39 Hawk sources are coincident with the position of known pulsars. For some of those bottom sources, maybe the supernova remnant contaminates the observed emission to some extent, although we're being pretty conservative here. Why do we care about having found 17 rotational pulsars in TeV data? Here's a picture of the number of pulsars we found in radio observations, for instance. There's 2,000 points on this plot. These are 2,000 systems observed by radio telescopes as bright pulsating emission sources throughout the Milky Way. Can we learn anything more by seeing 17 more sources compared to what we've seen here? And the answer to, as just mentioned, is yes, because of the beaming fraction. That is, a radio pulsar is a rapidly spinning neutron star here. It's spitting out beams of energetic radiation along the lines of these jets, along open field lines here. And you see this is bright pulsed emission. Every second or so you see a bright pulse in radio. But if you're over here, you see nothing. And the size of these radio jets is measured, and it's about 15 to 30%, depending on the age of the pulsar itself, which means that 70% up to 85% of pulsars, no matter how bright they are, no matter how close they are, no matter how powerful they are, et cetera, will never be seen in radio observations. They're hidden pulsar sources. On the other hand, TeV halos are bright, diffuse emission sources that move out for 30 parsecs and are produced by cosmic rays moving through the interstellar medium, producing gamma ray emission. Those sources can't be beamed. So I have to take those 17 sources that I found, the 17 sources that are coincident with the positions of known radio pulsars, and I need to multiply it by the inverse of that beaming fraction to get to the number of sources that I expect to be actually powered by pulsars that can be observed in the TeV sky. So once I do that, that 17 sources turns into 56 sources, plus 15 minus 11 or something like that. However, there are only 39 sources, right? So this is already a 1 sigma problem. I expect to have produced observed more TeV halos than Hawk has observed as total numbers of sources. Now this isn't a huge problem. Statistically, it's 1.5 sigma or something like that. Moreover, I have to deal with things like the possibility that there are chance coincidences in these 17 sources here, or that some of these sources are actually powered by supernova remnants, which probably affects 2 or 3. That being said, it's really hard to get away from the fact that almost all of the 39 sources that have been observed by Hawk thus far are powered by rotational pulsars. Let's look at what Hess observations say. Go back to that diagram we showed at the beginning of the talk. There are 12 sources that are called pulsar wind nebula. Now, nearly everything that Hess calls a pulsar wind nebula, I will call a TeV halo. That's just a terminology issue. They have 12 sources here that are pulsar wind nebula, and they're identified as such because they are on top of known rotationally powered radio pulsars. And I said about 70% of those sources, about 3 to 1 odds, that a source should be unidentified because it should not be on top of a known rotational power pulsar. And in fact, for the 12 sources they have, known PWNs, they have 36 sources that aren't firmly identified, a factor of about 3. And then they have some other sources that aren't associated. So a factor of 3 to 4 more sources are known but not associated with any radio source, as there are sources that are associated with radio power pulsars. Exactly the odds I told you should expect. It's very hard to get away from the argument that nearly all of these sources have to be powered by pulsar activity, and thus are TeV halos. Why are Hawk observations important? I've spent a lot of time talking about the Hawk telescope, about Geminga and monogem observations. But on the other hand, there's potentially 40 sources right here in Hess observations. There are more in Veritas observations. Why do I talk about the Hawk observations so much? And the reason comes down to this plot here. This is the distance to a TeV halo, or the radio pulsar that is powering it. This is on the y-axis. You get the spatial extension of the source that's observed. Remember, the TeV halos surrounding the monogem and Geminga pulsars were nearly 25 parsecs in radius. And the bottom of this plot, this dashed line, is the spatial resolution of the Hess telescope. If the source was smaller than this, they would think it's a point source. Here, they could see that it's an extended source using their atmospheric Cherenkov technology. What's interesting, though, is the top of this line. This is the line where the source gets so big that the small field of view of Hawk is no longer able to see the source. And that has to do with the detail of how atmospheric Cherenkov telescopes work. Mostly, you don't see gamma rays coming through the atmosphere and producing showers. You mostly see protons, cosmic rays, coming through the atmosphere and producing showers. The only way to get rid of that contamination is to zero subtract the entire sky. So you take all of the cosmic rays that come in, you subtract the isotropic component, and so if your source is big enough in your field of view that it looks mostly isotropic over your field of view, you accidentally subtract off your source as well. Atmospheric Cherenkov telescopes can't see any source that's bigger than about 0.5 or so degrees. If I put the Geminga and monogem TeV halos on this plot, they have a distance over here of about 200 parsecs. They have a size of about 25 parsecs. They are, in fact, invisible to atmospheric Cherenkov telescope technology, at least traditionally. That's something that some people here are working on in great detail to improve these, the sensitivity to these sort of extended sources. But on the other hand, Hawk is a water Cherenkov technology. It sees 35 degrees on the sky at a time. So it can subtract off a much bigger cosmic ray contamination area and look for much bigger sources. So this is a plot I'm sort of proud of. I'll explain it in a little bit of detail. This is the distance to a pulsar in the Milky Way on the x-axis. Y-axis is the spin-down energy of this pulsar activity, going from the kind of relatively low 10 to the 33, 10 to the 34 per second pulsars, up to the very, very energetic 10 to the 36, 10 to the 37 things that can be seen across the Milky Way. Every gray dot in this plot is a known radio pulsar. And it's a radio pulsar regardless of whether it's in the Hawk field of view, whether it's in the northern hemisphere, southern hemisphere. That just tells you the parameter space we're looking at in this talk. This is where pulsars exist in the Milky Way, are the gray dots. If that gray dot is surrounded by a blue or black dot, that is a source that's been observed by the Hess atmospheric Cherenkov telescope. If it's surrounded by an orange dot, it's been detected by the Hawk telescope, which is the water Cherenkov technology that can see bigger things. Now note, Hess is in the southern hemisphere, Hawk is in the northern hemisphere. It is geometrically unlikely they see the same sources, which is why they have not seen the same sources. You'll note that both of these telescopes are really good at seeing really high energy, so they're very bright, but very distant pulsars, because those things have small angular regions. They look kind of like point sources, and both technologies are good at seeing those. On the other hand, this is a source that becomes larger than the Hess field of view. Hess can't see anything below this blue line because it's bigger than their field of view of their instrument, so they can no longer identify this from background. Hawk, on the other hand, can see extremely large, extremely nearby sources. And so this opens a huge parameter space for detecting TeV halos from all of these gray pulsar dots here that can't be detected with atmospheric technology. So you can see there's a number of dots here. These orange dots are the ones. These are the 5 young pulsars observed by Hawk here. And this is their 2-year sensitivity curve. And after 10 years, they'll see farther down by about a factor of 3. And you can see there are many more gray dots in between the dashed line and the solid line than there are above the dashed line. So the future is very bright here. And so we said this in 2017. And after that, the Hawk collaboration looked at some of their sources. And they, in fact, identified 2 new TeV halos surrounding middle-aged pulsars. And they put them in at astronomer telegrams, shown here. And that's where these things exist in the parameter space. So we are starting to predict the observation of upcoming new TeV halos that can be observed here near the Hawk sensitivity curves. So it stands to reason that this is going to become more profitable as an adventure in the next few years. And we're going to observe lots and lots of TeV halo activity. The third implication is that the positron excess is due to pulsar activity. So what is the positron excess? Let's go back for a minute. Again, it is the fraction of electrons and positrons that are observed directly at Earth by experiments like Pamela on the left, the AMS observatory, which is on the International Space Station on the right. It is the fraction of those electrons and positrons that are antimatter, that are positrons, right? And so you can see that the rising positron fraction here in much more detail. These are AMS observations in red that have a great precision and show that this keeps going up to about 20% at an energy of a few hundred GeV. Now, very early on, when this was found in about 2006, 2007, it was pointed out that potentially this could be a symptom of dark matter annihilation. Dark matter annihilates to equal parts matter and antimatter, and if it does that, it produces as many positrons as it does electrons, and that could explain why the positron fraction rises. That produced about 1,500 papers to date. It's been an exciting field of study. It was also immediately pointed out in 2006 that pulsars produce, for the reasons we explained earlier, equal parts electrons and positrons in the pulsar magnetosphere by reaccelerating, producing pairs of electron positrons in a cascade. That produced about 20 papers over 10 years because the field of dark matter moves faster than the field of pulsar evolution. But very early it was pointed out that there were basically 3 uncertainties in this pulsar process. The first one is, what is the electron and positron production efficiency? If pulsars convert 100% of their spin-down power to electron and positron pairs, then pulsars produce lots and lots of electron and positron pairs. If pulsars only convert 0.1% of their total spin-down power into electrons and positrons, then they don't produce a high flux of electron and positron pairs. It was pointed out fairly early that the range that would explain the positron fraction had to fall between about 1% and 30%. The second thing we didn't know in 2006 is what the spectrum of those electrons and positrons were. It needs to rise sharply because the positron fraction rises sharply, which means the spectrum of electron and positron pairs has to be relatively hard, something like 1.5, e to the minus 1.5 to e to the minus 1.6 in the differential flux of these sources. I needed a hard electron and positron injection spectrum. And the third thing I worried about was how those electrons and positrons got to Earth. Those were the 3 uncertainties. So what did TeV halos do for those? Well, I just fit the Gaminga data with the electron and positron flux that has to produce it. I find that 9 to 27% of the total pulsar spin-down power has to be converted to electron and positron pairs, just to explain the intensity of the source that I found. So that answers the first uncertainty. To get the spectrum of the gamma ray emission that was observed, that correlates to a spectrum of electron-positron production, and that spectrum has to be about 1.5 to 1.9. Again, a very hard gamma ray spectrum, electron and positron spectrum that matches pulsar observations. I answer now the first 2 uncertainties in this model. And in fact, those were the 2 major uncertainties that were pointed out in 2006. I don't think I had to dig quite deep in the literature to find anybody who mentioned this third uncertainty, which is how these electron and positron pairs actually make it to Earth. But now that is the last key. And we know how electrons and positrons propagate through the interstellar medium. We have all those models. The same hadronic models, right, that explained the gamma ray emission that got to Earth. Cosmic ray protons were accelerated sources. They bounced around for a while. They produced gamma rays we could see. Sometimes they produce cosmic rays that get to Earth, and we record those. And so we can measure how efficiently those cosmic rays propagate through our galaxy. And so we do that with cosmic rays, primary and secondary ratios. So I'm not going to go through the details here, but they tell us that the diffusion constant is this number. Don't care about what this number is. It is a number. It is 5 times 10 to the 28. Don't worry about it. That is the high number in this scenario. So in that situation, that would be the answer. We would then use that number. We would calculate how efficiently the electrons move from something like the Geminga pulsar. Do they make it to Earth? How many of them make it to Earth? Do they explain the positron fraction? But maybe, again, the hadronic fairy tale is wrong. Maybe something different happens. And the leptonic story tells us that we need to reevaluate our paradigm. And in fact, that might be true. If we fit the morphology of the gamma ray emission inside this TeV halo, we can calculate how many electrons are 1 parsec away, how many electrons are 2 parsecs away, how many are 5, 10, etc. Doing that, we can calculate how efficiently those electrons and positrons move from the pulsar towards Earth itself. And so this was done by the Hawk collaboration. This is the gamma ray emission intensity as a function of the distance from the pulsar. Remember, the TeV halo extends to nearly 25 parsecs. Right here, this is the indication that the TeV halo extends to 25 parsecs. And this profile is quite sharp. Most of the emission is fairly concentrated near the center of the TeV halo. And using that, you can calculate the diffusion constant. And so they did that. And the diffusion constant was a much lower number. It's here quoted at a much different energy. It's about 1 times 10 to the 26. Actually, if I normalized those things to the same energy. And that would be a problem. If the diffusion constant is several orders of magnitude lower, that means the cosmic ray electrons and positrons propagate much less efficiently. I know the distance to Geminga, and I say, can an electron and positron make it against this very small diffusion constant? Can it fight all the way against a very hard diffusion constant and make it to Earth? The answer was no. So the Hawk collaboration said, well, Geminga can't produce the electron and positron flux here because those electrons and positrons can't make it to Earth. On the other hand, the observations of the TeV halo only go out to 25 parsecs away from the source. The distance from Geminga to Earth is 250 parsecs. That means 90% of the distance is in a region where the gamma ray observations don't tell us anything, right? The gamma ray observations tell us what's happening really near the source where we can see the gamma rays. It doesn't tell us about the rest of the journey. And if you know how diffusion processes work, the length that you travel goes as t squared, which means that 99% of the journey of a cosmic ray electron and positron happens in the region between 25 parsecs away from the source and 250 parsecs away from the source. So the key question is, what is the diffusion constant here? Here I know it's low. My hadronic models tell me that throughout the universe as a whole, it is large. Which one is right for most of the parameter space here? There are 2 ways you could solve this. You could extrapolate the low diffusion constant from the immediate region surrounding the source, extrapolate it up by a factor of 10 until it gets to Earth. And in that case, you find that electrons and positrons can't make it all the way. They lose energy too fast. It takes too long. It's too hard to diffuse. On the other hand, you could also take the hadronic models and extrapolate that down and say that the diffusion constant for most of that journey, the region from 25 parsecs to 250 parsecs, is efficient. And then you found the opposite story. The electrons mostly diffuse through a region where diffusion is very efficient. They make it to Earth very effectively. They make it outside of the TeV halo, which is small, and then they diffuse efficiently to Earth. And then here was the answer you got for the contribution of pulsars to the positron fraction. They do explain the data. And now this would be kind of messy. You would have to deal with different models, different assumptions, and you'd have to argue between yourself about fundamental physics. Fortunately, you can use TeV observations and again solve the problem. In the TeV observations we wanted to use, we're just answering the following question, which is, if Geminga can't produce the electrons and positrons, what can? It would have to be a source that's much closer, right? It can't be 250 parsecs away. It would have to be 20 parsecs away or 30 parsecs away. And the scenario is even worse than that, because the measurements of the positron excess don't only go up to about 200 GeV, but we've seen measurements now recently of electrons all the way up to energies of 20 TeV, 100 times higher in energy. And a statement that I won't be able to defend, but I will just state, is that higher and higher energy electrons lose their energy faster and faster to things like synchrotron radiation or inverse Compton scattering, which means they travel less distance. So at 20 TeV, a source that produces electrons that could fight through a very low diffusion constant and make it to Earth at very, very high energies would have to be extremely close. It could only be about 10 parsecs away or something like that. In fact, here's a source that is 200 parsecs away and has a very, very hard electron spectrum, e to the minus 2, e to the minus 1.5, e to the minus 1, which is the hardest electron spectrum you could potentially really imagine making. This is what the gamma ray spectrum, or the electron spectrum of that would look like at Earth after you diffuse the source to Earth against a low diffusion constant. And you see you can only produce electrons that make it to Earth up to an energy of about 2 TeV or so. To make a 20 TeV electron that makes it to Earth, the source could only be about 10 or 20 parsecs away. And we know that we know of no sources that are 10 or 20 parsecs away that have the same power as Gaminga, are extremely bright TeV emission sources that we've somehow missed in every other wavelength. So the most reasonable explanation then is that the diffusion constant for most of the journey, for the 25 parsecs out to 250 parsecs to get to us, is quite high. And in which case, pulsars do appear to explain the positron excess. All of the three assumptions have now all been met. And in that case, this is the most reasonable assumption. And I think going forward, if you want to do dark matter model building or something like that, to explain the positron excess, you need to explain why this scenario is not true. So to kind of talk about where we are in terms of the observations thus far, we used a fairly limited set of assumptions, which I've kind of color-coded here. And we've gotten pretty significant constraints out of them. We assumed that the TeV gamma ray luminosity that I got surrounding a pulsar is proportional to the spin-down power. And we normalized that to the Gaminga pulsar. If we did that, we found that pulsars explained most of the diffuse TeV gamma ray emission throughout the Milky Way, explained that 15 TeV data point from Milagro. Additionally, if the high energy electrons are trapped inside of the TeV halos, if they get stuck when 25 parsecs away, then they produce bright gamma ray emission near these sources. And we found that most of the Hawk sources and most of the Hess sources have to be produced by TeV halos. They have to be powered by pulsars. Also, if we assume that the lower energy electrons propagate farther and they escape from the TeV halos, make it into an interstellar medium and propagate effectively, then we found that pulsars must be the powering source that explains the positron fraction. Questions? What's the future of this field, besides involving flying cars and robotic dogs and other things that look cooler than what I'm talking about? Anyway, the future of this field is extremely bright, and that's something I want to stress. Already, we found about 20 or 30 sources with Hawk. We found about 30 or 40 sources with Hess. And we're already measuring key parameters of pulsar activity from those sources. So this is the age of a pulsar in thousands of years. This is the number of sources that have an age that's greater than that. And these are different models with different initial pulsar models, going back to those pulsar population synthesis models and kind of tweaking some parameters a little bit and seeing, can we constrain pulsar population synthesis models with TeV halos? The answer is yes. If the initial spin period is 300 milliseconds, then we can only explain this many pulsars. We, in fact, force ourselves into models where pulsars are born spinning very rapidly. We start to answer some of the uncertainties in pulsar propagation. And we don't have to worry about things like beaming fractions anymore, because we can see all of these sources. The same is true of Hess observations. The future of this is brighter. Hawk now has about 30 sources. In 10 years, Hawk will have about 100 sources. That's just numerology and the increased sensitivity. Hess right now has about 40 sources. The Cherenkov telescope array is a new advancement in atmospheric Cherenkov technology. This will take about 40 sources and move it to about 200 sources throughout the Milky Way, and actually be able to detect a number of sources in the large and small Magellanic Clouds as well. There's some evidence right now, just at about the 2 sigma level, that it's not only young and middle-aged pulsars that produce TeV halos, but in fact millisecond pulsars might also power TeV halo observations. So this could give us new clues into understanding binary evolution. Finally, we haven't talked about the modeling really at all, but we do have something weird, right? The diffusion constant near energetic pulsars is very, very low for reasons that I have not yet explained. and for reasons I'm not going to sufficiently explain here. In most of the interstellar medium of the Milky Way, the diffusion constant is really high, which means that the pulsar itself must be producing a region with low diffusion, must be constraining diffusion near it. In fact, there are models of that, and we built the first one. I think it has a lot of uncertainties at the moment, but it is something. And this is a model where cosmic rays actually produce their own self-generated turbulence. And what it does is explain much lower diffusion constants, again, by about 3 orders of magnitude. Here's the normal diffusion constant up here. Here's what the diffusion constant is very near a pulsar as the pulsar ages. And so this gives us new opportunities to understand how cosmic ray magnetic fields are generated, what actually produces cosmic ray turbulence and cosmic ray propagation inside of a galaxy. Also, we might understand these things at different wavelengths. At the beginning of this talk, we went from X-ray pulsar wind nebula, radio pulsar wind nebula, and we said that these are different than TeV halos. On the other hand, there should be radio and X-ray halos. They have the same morphology. There's high energy electrons in this region. There are magnetic fields. We should be able to detect this at X-ray energies, at radio energies. And the first object is possibly detected, this G327 object, which has 2 different pulsar wind nebula, what they call a compact pulsar wind nebula, and then a diffuse pulsar wind nebula, which is the size of its own TeV halo, much bigger, softer spectrum, lower energy electrons. It looks like we might have the first opportunity to see these as multi-wavelength sources. So I'm going to conclude and open for questions. TeV halo observations open up a new window into understanding Milky Way pulsars, into understanding their dynamics, into understanding what produces most of the emission in the TeV sky. The early indications of these are already really exciting. TeV halos produce most of the TeV sources that are observed by both atmospheric Cherenkov telescopes and water Cherenkov telescopes like HAWK. TeV halos dominate most of the diffuse TeV emission that's seen across the galactic plane and are going to be the most important source that we see in TeV astronomy going forward. And it also appears to give us strong evidence that the positron excess is due to pulsar activity. But the future implications are even more exciting. It gives us indications of how young pulsars evolve. It might give us indications of how millisecond pulsars evolve. It tells us things about cosmic ray diffusion. And though I didn't get to talk about it in any detail, this also gives us new information about the sources of ice cube neutrinos, which are produced by high energy hadronic sources, and also gives us new constraints into TeV dark matter candidates, because I now know what is producing most of the TeV gamma ray emission in the sky. So I'll open here for questions, but I just want to stress that I think the future of this field, stressed only based on empirical observations right now. We've taken empirical observations and gone very far already. But when we start understanding the models over the next decade and getting new observations to test those models, the field is going to kind of explode dramatically. So thank you.
Is there any limit to the speed of rotation of one of these things?
Yeah. Yeah, so there's a fundamental breakup velocity. There's a breakup velocity. The gravitational potential of a neutron star at the surface.
Gravity isn't strong enough to keep them together.
Right. So it can move up to about 70% of the speed of light. So it's a 10-kilometer object that moves about 70% of the speed of light on the surface. If it moves faster than that, it will break up. That is, I think it's 753 rotations per second or something is the fastest you can do. So it's some number like that.
So they pick up their angular momentum simply from the inflow.
So there are two different mechanisms. The first is in young pulsars. It's some asymmetry in the kick when the supernova goes off and material collapses back onto the neutron star itself. So that gives it angular momentum. That tends to only produce pulsars that move at about a couple rotations per second. That's that 50 millisecond rotational period, so 20 rotations per second. The second is if the pulsar has a binary star companion. And that binary star starts accreting material and angular momentum onto the pulsar. And that's what produces the extremely rapidly rotating millisecond pulsars. And those are the ones that we see moving 750 times per second or something like that.
Really asymmetric radially.
Yes.
Is there a reason for that?
Potentially. We've thought about it, and some of the explanations are a bit complicated. This mechanism where pulsars change their diffusion constant only works well when the gas density is really low. So asymmetries in the gas density near a pulsar source, especially a moving pulsar, could explain why the diffusion constant is not totally homogeneous surrounding the source. I don't expect that the diffusion constant is just a radial thing when I put it into a real and complex interstellar medium. So I think learning about this process in more detail will start to explain why some TeV halos look different than others. We'll start to build up kind of a population level statistics for these sort of things.
Any further questions?
So you mentioned that we should be able to see these things in X-ray energies.
Mm-hmm.
Very large.
Yeah.
I mean, how bright would they be? Are we not seeing them just because they're much bigger than the field of view of a telescope?
Yeah, so we took the first observations with XMM Newton. I think the observations were taken 2 weeks ago. I don't know if the data is even down, or I don't know how X-ray observatories work. But we had a proposal which we got observations for. The goal is to look at TeV halos that are quite distant, because I want these sources to be relatively small, so that XMM Newton can resolve them. Right, the surface brightness doesn't really go down, and the source just gets smaller and smaller and fades away. So the best bet is to look for the TeV halos surrounding pulsars that, or by TeV halos now I mean at X-ray energies, the X-ray halos surrounding pulsars that are 5 to 10 kiloparsecs away. And so those were the goals of our targets.
Okay, so no more questions. Thanks.